Hello again. So just to remind us, the next session will be given in English, so la prochaine session va être en anglais. So we carry on with our TED journey, and now we have a speaker who's going to talk about how to deal with streams in your applications. So please give a warm welcome to Konstantin Knauf.
Good morning, bonjour. Thanks for the introduction and thank you for the warm welcome. My name is, let's see if I can do this. Point it there. Okay, apparently. All right, yeah, my name is Konstantin. I've been working on and with Apache Flink, a stream processing technology for the last 8 years at consultancy, two startups, went through 2 acquisitions, and very recently, January basically, I joined Confluent, the company founded by the original creators of Apache Kafka, which probably more of you know than Apache Flink. And well, we joined Confluent to bring Apache Flink into their cloud product, Confluent Cloud. And today, I basically want to talk about I want to introduce both of these technologies to you, and I want to convince you, I want to show you why it makes a lot of sense to use these 2 technologies together, and why it makes sense that we are bringing them together in Confluent Cloud. In the end, I'll also have like 3 slides on what we are doing in Confluent, but everything else will be primarily trying to tell you what data streaming is about. Maybe can we do a quick survey? Like, who of you has been in contact with Apache Kafka before? Yeah, many. What about Apache Flink? Only very few. Okay, good. Because I only have a few slides on Kafka, kind of a refresher, and the majority of the presentation is going to be about Apache Flink, which is also where my expertise lies. So why should you actually care? So customers today expect personalized real-time experiences. They expect fraudulent transactions to be caught before they hit their bank account. They expect updates in their transportation apps to happen before the train is delayed or before they miss the train. Gaming, gambling, entertainment, all of these industries are disrupted by companies that really focus on a superior customer experience based on real-time data-driven decisions and actions. And for this, companies are really rethinking how they do their data infrastructure. They want that their data can flow seamlessly between Was something wrong with the slides? Did you see my speaker view? Ah, that makes sense. Well, it doesn't make sense, but yeah, I think that was the slide we were on. Awesome. Yeah, so companies are really rethinking how they do how they set up their infrastructure to facilitate these kind of applications, and the kind of applications that these companies are building with Apache Flink, with Apache Kafka, they broadly fall into 3 categories. The use cases fall into 3 categories: data pipelines, which is mostly moving data in real time from A to B and transforming it continuously on the way. You can think of ML pipelines, but also just simple data lake ingestion and just going from JSON to Parquet and things like that. Then we have real-time analytics, where it's about providing views on data, on real-time data, that matches the downstream consumers and that serve front-end applications very well. So here we're talking, for example, about usage metering and billing, which really shows kind of the maturity of these technologies in terms of correctness and consistency. And then it also goes up to kind of general event-driven applications and microservices, where Flink is just used basically as an application framework. And the most common use cases there are in the area of fraud detection in banks, anomaly detection, cybersecurity, and things like that. Well, here you see another kind of broad spectrum of these use cases through different verticals. The technologies in this picture are basically Apache Flink for the stream processing itself, and the data is often coming from Kafka and going back to Kafka. Sometimes also databases, but Kafka and Flink work really well together here. And yeah, now I'm basically going to talk about these two technologies. We'll start with Apache Kafka, and what I try to do for both of these technologies kind of focus on the principles, the cornerstones that you need to understand to then understand everything else around them. So I want to bring you into a position where a lot of these things make more sense to you, and you have a much easier time learning these technologies. So for Kafka, it starts with streaming. And streaming is about capturing events in real time and processing them continuously in real time as they are produced or as you receive them, as opposed to buffering them for a while and then processing them in a batch or processing them on request. And most of the data in the world is actually streams. It's continuously produced, and there are no batches in real life. But you can also store streams for a long time and actually then do historical data processing on top of these streams. And that is where basically bounded stream processing or batch processing comes into the play. So in some sense, at least like conceptually, stream processing is just, or batch processing is a special case of stream processing. It's only kind of half the truth, because batch processing is much more efficient than stream processing if the data set is bounded. But conceptually, you can think about it this way. The next cornerstone are events. And well, events are not only used in streaming, but in general, event-driven and domain-oriented design. And events are a natural way to reason about the world. If you, outside of technology, you also think a lot about events. And events usually, or they indicate something that has happened in the past. When something happened is important, who did it, who was involved, and what happened. And they are mutable, which makes sense because you cannot travel back in time and change something that has already happened, and events indicate something that happened in the past. And lots of events together make up a stream. Here's an example of an event from the Confluent Cloud message browser. I think we're seeing page views here. Then in Kafka, the basic kind of storage abstraction are topics. You can think of a topic as a message queue, or you can think of a topic as a table. It's a little bit different, but basically it's the table in Kafka. And you can read and write events to a topic. The consumers, well, to the left, that should be producers. The producers can produce events independently. One producer can produce events to many different topics. And the consumers can consume these events. And the important thing is in Kafka that consumers and producers are completely decoupled from each other. So a consumer doesn't need to know which producers they are. They don't need to be in the same place at the same time. And if one consumer consumes an event, that doesn't mean that other consumers cannot consume that anymore. Consumers can coordinate themselves to kind of share work, but basically every consumer itself decides where to read events in such a stream. Inside one topic, or a topic is then further split up into partitions, and each partition is a completely or strictly ordered set of events, and append-only logs. So you can only add to partitions, you cannot update anything there, and partitions are also the level at which work is replicated across Kafka procars, which are kind of the worker nodes in a Kafka cluster. And here we basically see three topics with 3 partitions each, and how they are distributed across the procars. But each individual partition is then also replicated, usually at least with a replication factor of 3 across these procars. So here we see now a view on one topic with 3 partitions and a replication factor of 3. So for each partition, you have one broker that is the leader and 2 brokers that are the followers. And now if one broker would go away, you would still have a replication factor of 2, and to actually have data loss, all 3 brokers would have to go away. Sure, but what's the point of all of this? The idea, as I mentioned earlier, is to establish Kafka really as what we call it at Confluent, the central nervous system of your application. So you connect your operational systems to it, you connect your SaaS applications to it, you connect your analytical databases to it, and Kafka, through the way it decouples consumers and producers, can become a central hub in your organization, in your data infrastructure, where your most important events are stored and shared and governed across the organization. Now, coming to Flink, an introduction in 3.5 acts. Flink has generally been quite successful in the last 3 years. It has seen a rising adoption for a long time, but in the last 3 years we can really see this taking off, and a lot of it is due to these 4 factors. So Flink comes with a very scalable and robust runtime for stream processing that can achieve high throughput and low latency at the same time for stateful computation, and we'll learn more about what that means. It's as fault tolerant as Kafka is, and it provides lots of different APIs that appeal to different types of developers, to data analysts, to data engineers, as well as application developers with the SQL, Python, and Java API. And all of these APIs are unified across batch and stream processing. So you can write your program once, and then depending on the nature of your data, whether it's bounded or unbounded, you can either run it using stream processing techniques, or you can run it using batch processing techniques. The 4 cornerstones here are quite similar to Kafka. So it starts with streaming. I'm not going to say everything again here that I did before. It's exactly the same concept. The Flink reads from sources. This can be Kafka, and it often is Kafka. About 80% of Flink users use Kafka as source or sink. But it can also be files or databases, for example, for lookups during enrichment, or it can be directly, you can also directly call the GitHub API and stream the commits from the Flink GitHub repository, for example. And data is usually synced either to a message queue or to a database or S3 directly. Inside, or if we zoom into how a stream processing program looks like, it's usually, a graph consisting of operators and connections between these operators. And this is in Flink what we call the topology or job graph. The job graph in Flink is then parallelized across multiple instances, and the stream is partitioned. And that it's very similar to how Kafka works, and it's one of the reasons why they work so well together, because Flink relies on being able to read streams in parallel, and Kafka makes this very easy. So here we have a source operator that reads some events in different colors. They are then forwarded to the next to the next operator, and this forward operation is kind of the simplest operation that you can have in Flink, and Flink makes this very efficient by pipelining these together or fusing these operators together. And we then filter these events. Here, in the second operator, we filter out all the orange events. And then in the next stage, we group them by their color. So for this, we need to actually reorganize the stream a little bit. We need to do a shuffle between the different operators, and this is much more expensive because for each of these, for such a shuffle, all the events need to be serialized and potentially need to be sent over the network, or most of them will have to be sent over the network. Depends a little bit on how you deploy it. But it's much, much more expensive. Serialization is always the most expensive thing. Well, obviously not always, but in real world it often is. And then this operator here can do something with all the events of the same color. And since we've brought them together, we can, for example, count them. And then downstream, we would, for example, send the count for each color. And here we're changing the parallelism of the sync to 1, just for illustrative purposes. In reality, it would probably just stay 2. And this is then called a rebalance operation in terms of the data exchange mode. Now, this whole application that we just went through can be, for example, written in Flink SQL. So if we have an insert into results, and that defines where we send the results, we have a select and a group by statement that defines that we group by color and count. And the where clause defines the filter operator, and, well, the from clause defines the source. So this is basically how a Flink SQL program is translated into a data flow graph and parallelized. We don't only have the SQL API. There is a programmatic equivalent to the SQL API, which is called the table API. It's not. It sounds like DDL, but it's not DDL. It's basically a link-style query language in Java and Python, where you can write programs that you where you can write slightly more programs than you can write in SQL. Yeah, many people enjoy Java or Python more than SQL. And both of these build on top of a calcite optimizer and planner. This is very important because in the other API, the data stream API, you actually physically define this data flow graph. So you put in a functional API, you put each of the operators together. And in the table API, this is done by the optimizer. So it automatically does things like projection pushdown, filter pushdown. It reorders joins to be more efficient. And that from my experience as kind of a solutions architect for Flink, this is super important for many use cases because it's hard to always remember to do projections early, to do filters early in the stream, and that can mean like really factors and of performance and resources. Yeah, so there are basically these three main APIs: table API, SQL, and the data stream API. And they are just different ways to define and to describe this data flow graph. In the end, this data flow is sent to from the client, or this job graph is sent from the client to the job manager, and the job manager either acquires, finds, or starts the resources to run this job. And for that, he launches or finds task managers, which are the worker processes. And the individual tasks that we have seen, the individual vertices of these parallelized job graphs, they are then deployed into task slots in the task managers. And each of these task slots can make progress independently of the others, which is one of the important factors that make Flink so resource efficient, that we have this kind of share nothing architecture. Of course, we've seen there are these data shuffles, so these individual task slots need to communicate with each other, and they need to be able to exchange data, and that happens directly between the task managers through network stack, or Flink's own network stack, that is, which is Netty based. Which brings us to the next cornerstone, state. So I've already mentioned state once. We can take a look at our example again and see where do we have state here. So the filter operation doesn't have any state. You just have an event. All the information that you need to perform this filter operation is the event itself. So there's no state here. The count operation, on the other hand, has state. The count per color is the state. And in Flink, state is always local, as opposed to in a traditional application where you usually have a stateless web application, for example, that talks to a remote database. And this is really the key to Flink's performance, that all these state updates happen locally, either on the heap or in a local RocksDB instance. So there you have two different state backends, as it's called in Flink, one on the heap, the other one on disk in RocksDB. But in both cases, it's local, and the durability and fault tolerance is achieved through snapshots, which we will talk about in a second. But basically, it's a remote backup to S3. The next cornerstone is time. And in stream processing, there are two different notions of time: event time and processing time, or wall clock time, as it's also sometimes called. The event time is when the event actually happened. The wall clock time or processing time is the time at which we process it. So if a transaction happens, then the time when the transaction happens is the event time. Processing time can be whenever someone processes this transaction. And streams are usually pretty much out of order in terms of event time. Sometimes they're more in order, sometimes they're very much out of order or delayed. In particular, if you're processing events that come from mobile devices or any other distributed infrastructure, then just through connectivity issues, you will have delays, and out of orderness, you will have delays because of upstream systems which have downtimes and need to be restarted or introduce delays. So in order for a stream processor to be able to provide consistent and correct results, we need to have a way to deal with this out of orderness. So the way we do this, and here basically processing happens from, right to left. So this is the event that will be read next by an operator, and these events follow. And if you look at the timestamps here, you can see that they are mostly in order, but also a little bit out of order. So if we now imagine that you have a window operation that tries to count the events within a 1 minute window from 1 to 2, then we have already been counting for a while, and now we're coming to the point where this window at some point needs to end. And the question is, when do we stop? Like, do we stop when we see the first event with the 2-minute timestamp? Do we keep on counting? When do we emit an event downstream? And this is where watermarks in Flink come into play. Watermarks are events that are system generated and are basically traveling through the job graph as part of the stream between the events, and they basically transport assumptions about the out of orderness. So here the assumption is that events are not out of order more than 5 seconds. So if we see an event with a timestamp of 1 minute 50, we can send a watermark of 1 minute 45. And this watermark indicates that no events with a timestamp lower than 1:45 will arrive after this watermark. Of course, we don't know whether that's actually the case. So there can be events that with a lower timestamp afterwards. Those events would then be considered late in Flink terminology, and there are different ways to handle late data. One common practice is to just discard them. But you can also send kind of refinements of the results afterwards. Overall, watermarks are really a way for you as a developer to trade off between latency and completeness. If you define a very aggressive watermark, you will have results earlier, but they will be incomplete. If you define a more conservative watermark, you will see results later, and but they will be more complete. There are also ways to do this kind of quite adaptively. For example, in our cloud offering, we have one that adjusts the out of orderness dynamically based on historical delays of the stream and kind of a histogram-based approach. But the more common thing is to just define a fixed out of orderness. Okay, I think I've skipped a few slides here. yeah, so watermarks make things happen when the time is right. Which brings me to the last cornerstone of Apache Flink, and this is snapshots. We have two kinds of snapshots. We have checkpoints, and these are automatic snapshots that happen periodically and are created by Flink itself in order to, as backups, as backups for fault tolerance. And they are very much optimized for recovery. Their format is optimized for recovery so that they can be taken quickly and that Flink can recover from them very quickly. And they are discarded automatically by the system. So it's nothing that you as a developer need to care about that much. You need to configure it, but you don't interact with them. A save point, on the other hand, is a manual snapshot that you as a developer trigger yourself. You control the lifecycle. You will discard it when you don't need it anymore. And their format is optimized for operational flexibility. So the idea is that you take a snapshot of your application, and then you can make changes to your application. For example, you can add an operator, you can change the schema of the state of an operator, you can travel back in time, you can migrate your application to a different data center, and all of that in a way that your state is preserved. So when you start it again, this application will start reading from the same position where it left off, and it will load the consistent state of all the applications. We will see an example of that in a second. So yeah, going back to our running example here, what kind of state do we have here that is snapshotted? Snapshots happen as we go through the stream, basically, or in the order of the stream. They happen through a process that is called asynchronous barrier snapshots. So we have checkpoint or snapshot barriers that travel through the whole job graph, and whenever an operator has seen all the snapshot barriers from all upstream operators, it will take a snapshot there. And this starts at the sources, and here the snapshot contains the offset of the Kafka partitions. The filter doesn't have any state, doesn't have anything to snapshot. The count will just be the counters for some of the colors for each of them, and the result, if we produce to Kafka, will be the Kafka transaction ID. Why do we need that? In order to achieve exactly one semantics, we produce to Kafka using Kafka transactions, and in a case of failure, we need to, and recover, we need to be able to continue producing to the same transactions. We might need to abort transactions, we might need to complete transactions that should be completed, so we always need to remember to which transactions we've been writing. An important aspect is that these snapshots are not a kind of stop-the-world event. These snapshots happen asynchronously while data is still being processed, and they happen incrementally, so you don't always need to take a snapshot of all your data. You don't need to send all your data to S3, which is very important because the state can actually grow very large. So we have Flink jobs that have tens or even 100 terabyte of state, and basically snapshotting that every minute to S3 wouldn't be possible. But with incremental snapshotting, that actually works because what matters there is the change of rate of the state, and it doesn't matter how big the state overall is. I already mentioned, Flink provides exactly once guarantees. What does that mean? It means that every event that Flink processes affects the state and the world around it exactly one time. It doesn't mean that every event is actually processed exactly one time, because if there is a failure, what happens is that Flink rewinds the whole stream to the last successful checkpoint, and it starts reprocessing from there. But events will only be produced and published downstream once, and they will only affect internal state once. So again, what is the point of all of this? How does it go together with Apache Flink, with Apache Kafka? Because all these event-driven applications and since many of you use Apache Kafka, you probably use Kafka streams, or you use plain Kafka consumers and producers. And you're probably thinking, yeah, well, I'm already building these types of applications. I'm already building event-driven applications. Why should I care about stream processing? And yes, that's right. You can build all of these applications directly with plain Kafka consumers and producers. But it's a little bit like building a web application directly on top of a file system, which you usually don't do. You usually have a database. And in the world of data in motion, which is the marketing-y term that Confluent uses for streaming and stream processing, the stream processor kind of fills the role of the database. So like a database, the stream processor provides these higher-level building blocks that make it, abstractions that make it more resource efficient, more secure, and most importantly, just easier to build applications on top of these streams in Kafka. At the end of the presentation, I will know where's forward and backward. So, how does Apache Flink on Confluent Cloud look like, or what are we trying to achieve here? As you might know, Confluent is the company founded by the original creators of Kafka, and Confluent has had a cloud service for Kafka for the last, I think, 4 years. And the main pillars, the main principles that guide our cloud offering are cloud native, complete, and everywhere. So we want to build a service that really is more than just bringing Kafka and the infrastructure to the cloud. We really want to move from, if you think about it, from an NFS to S3. Like it's very different to just move on-premise infrastructure to the cloud to really providing a cloud native experience, a serverless experience. And that's what we are striving for Kafka as well as for Flink. We also want to make this a complete offering. So not only Kafka and now Flink, but also the governance features around it, the security features around it, the connections. We want to build a complete data streaming platform. And we want to make this available everywhere, which means in all clouds, in all regions, and also on-premise. So for Flink, what does this mean? We think we're building the first truly native cloud service for Apache Flink. So there are already a few or hosted services for Apache Flink out there by the cloud providers, as well as, well, 1 or 2 startups. But we really want you to be able to focus on your business logic, on your applications, which really means just this piece of SQL, for example, if you're using the SQL API. We take care of all layers of the infrastructure from the operating system to the Flink framework. What does this mean concretely? So, for example, on Confluent Cloud, you don't need to, and you even can't specify a Flink runtime version or Flink version. You will always use the latest version, and we automatically do these upgrades under the hood. And that's not just like security updates or patch versions. This is the major updates of Apache Flink that we upgrade under the hood for all of your running applications. There's also no way in Confluent Cloud for you to specify a parallelism for each of these operators or even globally. It's really zero knobs. We have a so-called autopilot that periodically, or I think every 10 seconds, monitors the load on your stream processing jobs, on your Flink jobs, and adjusts the parallelism on a very fine granular basis so that it always keeps up with all of your sources. It also means that you don't actually interact with checkpointing or state backends or task slots. So all these runtime concepts are nothing that you need to worry about in our cloud offering. The billing model is, of course, also then following the serverless paradigm with usage-based billing and scale to zero. So if you provision a compute pool, which is our concept of a virtual cluster or a virtual data warehouse in the cloud, and you don't use it, you don't pay for it. Yeah, and we are integrating Kafka and Flink very closely in our cloud offerings. So if you are using Confluent Cloud or you're using Kafka, then you know there are environments, there are clusters, and there are topics, and we automatically make all of this data immediately available on Confluent Cloud or in your Flink catalog, so that you can immediately start querying this data without any manual schema work or things like that. And finally, well, we want to be available everywhere. In reality, we just entered public preview. So as I mentioned, I joined Confluent early this year, and we've been working kind of around the clock on this. And at Current, our main developer conference in September, we entered public preview. So if you are a Confluent Cloud customer or you sign up for free, you can already use it today on AWS in 4 regions. And as we approach general availability next year, Q1 next year is the target, we will be available in Azure and Google Cloud as well. Yeah, and that already brings me to the end of this presentation. So we have a little bit more time for questions than I was targeting. Yeah, happy to answer any questions on Apache Flink or Kafka as good as I can. Thank you.